Hi everybody. Today I get to talk to you about triangle classification and triangles in general. Just about time to start talking about triangles in this geometry class. And we're going to start by classifying triangles. We'll start by classifying a triangle by virtue of its sides. A triangle could be scalene. In a scalene triangle, no two sides are congruent. I tried to draw a scalene triangle here. Let me call this triangle ABC, just so we can talk about it, and indicate that AC is the shortest of the sides, and BC is bigger than that. AB is bigger than that, and BC is the largest of these three sides. And because these have different length, different marks, we'd accept that they have different lengths, and we have a scalene triangle there. A triangle could be isosceles. Isos in ancient Greek says equal, and when two sides are equal, as in this triangle shows, two sides equal in measure, then we would say we have an isosceles triangle, a triangle with two congruent sides. What's an alternative to that if it's not scalene and it's not isosceles? If a triangle weren't scalene or isosceles, it could be equilateral. Notice how you spell that, with the I, equilateral. People want to say equilateral, but it's not. And it has all three sides congruent. I tried to sketch an equilateral triangle over here. And to indicate that it's equilateral, we could put those number of marks on each side, or two on each segment if you like. How can a triangle be classified by its angles? Let's talk about that too. If we classify a triangle by its angles, it could perhaps be acute. An acute triangle, all three angles are acute. Now I was thinking how to draw such a picture, but wouldn't this equilateral triangle also be an acute triangle? Yeah, how big would these angles have to be, I wonder? That's something we ought to talk about. If a triangle weren't acute and we were trying to classify it by its angles, what else could happen? A triangle could be a right triangle. And for a triangle to be a right triangle, it's a triangle with one right angle. If I wanted this triangle ABC to be considered a right triangle, I probably ought to put a mark like that so you would know that angle B is a right angle. Therefore, we'd know that this is a right triangle. If it were not acute or were not a right angle, what kind of triangle could we have? An obtuse triangle. An obtuse triangle has one obtuse angle. For example, angle Q could be obtuse. And this might be an isosceles obtuse triangle. I guess these two sides might be congruent, but we don't know that. And we're going to talk about, though, what are the important parts of an isosceles triangle. And here I declare this to be an isosceles triangle. Let's call it triangle ABC. And say that these two segments are congruent. Mark it that way so that we know that AB is congruent to AC. And want to discuss with you the important parts of an isosceles triangle. An isosceles triangle has legs. And as a man stands, his legs form an isosceles triangle, and the legs are the congruent segments. So the legs on this one would be AB. And I'm going to go ahead and say that AB is congruent with, the legs of an isosceles triangle are necessarily congruent. AB is congruent with AC. And it has a base. And a lot of people think the base should be on the bottom, but that's not necessarily so. The base of an isosceles triangle is just the side that's not one of the congruent not one of the congruent legs. So the base on this one is just segment BC. It's got base angles also. Make a note about that. Which ones would be the base angles in our triangle? And they are the angles that are on the base, and since the BC was the base, the angle at B and the angle at C are in fact the base angles. And something we're going to learn, what do you think about those two angles? Is there a relationship they have with each other? As a matter of fact, they're congruent, aren't they? That's something we're going to prove soon. It's an important idea about an isosceles triangle, that the base angles are necessarily congruent. I'm going to say angle B, in fact, would be congruent with angle C. Those are the base angles of this isosceles triangle. It also has a vertex angle. And the vertex angle is the one that's not the base angles. So the vertex angle here would have been angle A. We're going to work so much with isosceles triangle that it's important that you know these parts. Here's a little instance of what we could do with an isosceles triangle, how we can write some equations. A picture is such a good idea when you're trying to figure out what kind of equation to write. What should I do with these expressions? What kind of equation I can write? It tells me we have an isosceles triangle, ABC, with base BC. So let me declare that to be the base. This will be the vertex angle, and these are the congruent legs. And let me label the data that we're given here. AB is 2x plus 8. BC is x plus 4. While AC is 4x minus 4. And we're supposed to find some way to relate these expressions to come up with the value, to write an equation, come up with the value of x, and we're going to come up with the perimeter of the triangle. And probably a good idea is for you to pause it and figure that out yourself. But I'm going to jump right in. It's pretty obvious right away that if these are the legs, then they've got to be congruent. I might even write that AB is congruent with AC. By virtue of this being an isosceles triangle with base BC. And that tells me that 2x plus 8, the measure of AB, must equal the measure of AC, 4x minus 4. And so we could find the value of x this way. I'd subtract 2x from both sides. You probably would also. That leave me with 8 here. And as I take 2x from both sides, I'll have 2x here minus 4. Bring that negative 4 to the other side. Now I think that 2x is equal to 12. Divide both sides by 2, and we realize that x is equal to 6. What good is that going to do me? Let's see. We're supposed to find the perimeter of triangle ABC. We'll do just that. I'll find the length of AB first. And if x is really 6, then that'll be 12 plus 8, therefore 20. And AC, I know that AC should be the same amount. Let's check on that. If x were truly 6, 4 times 6, there's 24 minus 4. Yeah, it's also 20. That's a good thing. And then side BC, if x were truly 6, and that BC would have been 6 plus 4, therefore 10. So we can safely declare the perimeter of the triangle is 50. Just adding up those sides. This last little part on this page, make a sketch of each of these if possible. There might be some that cannot be done. For example, could you draw an obtuse scalene triangle, PQR? Do so. I drew an obtuse scalene triangle, PQR, and if anybody wanted to argue with me, I'd say, well, this angle is obtuse, and it does apparently look like one, and let me say that this segment is smaller than that one, and that one's smaller than this one, and then you'd have to agree that we have an obtuse scalene triangle. How about a right isosceles triangle? Are those terms mutually exclusive? Can you have a triangle that's a right triangle and be isosceles at the same time? Yeah, let's think about that and make such a sketch. I meant to draw a right isosceles triangle XYZ. And if I declare this to be a right angle, and that ZX is in fact congruent with XY, then you'd have to agree that that's an isosceles right triangle. How about an obtuse equilateral triangle? I want to draw an obtuse equilateral triangle, but as soon as I make it be equilateral, this triangle ABC, as soon as I make it be equilateral, it can't be obtuse. I think that these angles are all three less than 90. They're all three acute. I think an equilateral triangle is in fact equiangular. I think these angles would be congruent to one another. In fact, I believe they're going to be 60 degrees apart. So I don't think you can have an equilateral triangle that's also an obtuse triangle. If it's got an obtuse angle, it can't be equilateral. These are what we'd call mutually exclusive terms. Let's look at this other page, see what we can figure out. Here we have what's called a congruent statement. And it's a big deal for the next little while in our class. This tells me that triangle ABC is congruent with triangle XYZ. And the question we ought to be asking ourselves right away is, what does it mean for triangles to be congruent? Are they equal in measure? Then how do you measure a triangle? Let's talk about this. List the sides that must be congruent. If these two triangles are congruent, I know that they are identical in every way. And by virtue of the way that these things have been named in this congruent statement, we can know that side AB has a corresponding part that must be congruent. And by virtue of being in first and second position, that would match with triangle, with segment XY. Those must be congruent. Likewise, what about segment BC? BC, being second and third position, must match with YZ. Those must be congruent if this is a well-written congruent statement. And let me go with another segment. What if I talked about ZX? ZX in third and first position must be congruent with segment CA. Just by virtue of this congruent statement, we know that these corresponding sides must be congruent. It also asks me, list the angles that must be congruent between these two congruent triangles. Let's walk down that path. What if I talked about angle BAC? Who would angle BAC be congruent with? And we don't have a picture to go by, but what we've got is a congruent statement, and it tells us a great deal. If I went BAC, that's second, first, third position, that would match with second, first, third, angle YXZ. Let's name all three pairs of congruent angles. How about if I went with angle ABC? Angle ABC, well, that would match with angle XYZ in the same order. There's probably another pair of angles I've not yet talked about. How about if I said angle YZX? Who's angle YZX congruent with? And second, third, first, therefore second, third, first, that'd be BCA, huh? Angle BCA. So what you got to be realizing is it's important that we name these very carefully, or these corresponding parts won't be matching up as they should. And here's a good example of how we kind of name those kind of congruent triangles very carefully. Look at this instance, for example. Check the figure out right. Take care to name the triangles that appear to be congruent in the proper corresponding order. And I start off by talking about triangle AEF. You confirm that's point F right there, don't want to lose it. And here's triangle AEF. And I know everybody in the room says, well, that one's going to be congruent to this triangle over here. They appear to be congruent. But what we have to do well is name them in the proper order. And I would tell you, the angle at A appears to match the angle at B, just for appearance's sake at this moment. So when I start with A, I'm going to start with triangle, and start with the letter B. And AE, this segment, matches this segment BC, so I'm sure that's going to go that way. And this angle at E is clear to me that it is congruent with this angle at C. So I'm sure that we're off to a pretty good start. When it goes AEF, it's going to match with triangle BCF. And you might have been thinking those two angles at F are congruent because they're vertical angles, aren't they? So this is another valid congruent statement, and we can infer things from this. How about this one? Triangle CAE. Let me shade that triangle, this kind of larger triangle CAE, and it does have a congruent partner there, doesn't it? It's important that we name it well. CAE, I think CA matches with EB. I'm going to start by saying triangle EB, and when I went CAE, I think that's going to match with EBC. But let's test something there. Take an angle from this one, and I'm just arbitrarily choosing an angle. Let me say angle EAC. What angle would that have to be congruent with? And this is just a way to test things. If I said EAC, that would have to match with CBE, angle CBE, and angle EAC, this angle. Does that match with EBC, this angle? And I think we would agree that, yeah, those are corresponding, they are congruent angles, so I think we've named this correctly. And that's a way you can check stuff, be sure you're getting it right. It's a pretty good idea some of the time. Triangle ADC. ADC. This pretty big triangle. You don't got to shade it, but this triangle ADC's got a congruent partner, apparently. And what matches AD is BD. I'm sure there are other ways you could think this through. ADC match with BDE. If in fact this is true, and I believe that it is, who would AC have to be congruent with? And just using this congruent statement, first and third position should match with first and third position, that'd be BE. Let's check that sketch and see if that's true. Is it true that AC matches BE? Yeah, so this is properly done, I bet. One more time with feeling. This talks about triangle ABF. Is there another congruent triangle with triangle ABF? And if you thought ECF, I'd say no, those are different sizes. However, there is a statement that could be made here. Let me make it. You might not like it. I say triangle ABF is congruent with triangle BAF. Or potentially could be written that way. And you say, well, hey, that's not good. You just move some letters around. But look what that would imply, truly. Who would AF have to be congruent with if this congruent statement were true? And you say, well, AF in first and third position would match with BF, huh? So in fact, this would, if this was a valid congruent statement, then that would force this triangle, triangle BAF, to be isosceles. And these would be the base angles, and we would know more about it than we know right now. Now we're going to get a chance to look at corresponding parts and write some equations. Read through this, pause the video, get a look and see what kind of equation you think we can write. You could make a sketch, I guess, but I don't think it's really necessary. Here's what's going on to me. Know that these two triangles are congruent. Let me make that look like they're congruent. And it tells me all about the three sides of triangle ABC, but it only tells me a little bit about triangle OMN or MNO. It only tells me about side OM. And I'm looking for somebody to be equal with someone else. And by virtue of those positions OM, we must know that it has a corresponding segment here. OM being in first and third position, third and first, would match with CA, wouldn't it? That's a big deal. I'm going to make a note of that. By virtue of the corresponding parts, segment OM is congruent to segment AC. This kind of question is going to happen a lot. I want to give you one side out of triangle MNO, and you check out who that corresponds with, and then we can get an equation. OM, 5x minus 5, must be the same as AC, and AC is 3x minus 1. So we'll solve that little wimpy equation, see what comes, and subtract 3x from both sides. I have 2x minus 5 equal to negative 1. Add 5 to both sides. Now I think that 2x is equal to 6. Oh, excuse me, 2x is equal to 4. Divide both sides by 2, and I got x equal to 2, just 2. Now notice it asked me to find the value of x, and that was easy enough, but then the perimeter of triangle MNO. But I only know one side out of triangle MNO. But come along, and I think you have a good idea about this as well. Let's get the lengths of the sides of triangle ABC. Bearing in mind that x is equal to 2, AB would have been, oh my goodness, I hope that we've been interpreting that as 2x plus 1. I meant for it to have been that. If AB is 2x plus 1 and x is equal to 2, then AB would have been 5. Sorry about my typing error there. And then what about BC? If x were truly 2, then BC would have been 7. And what about AC? If x is truly 2, then this would have been 3 times 2 minus 1. That could be 6 minus 1, also 5. So we got an isosceles triangle, don't we? And the perimeter of triangle ABC would have been 17. But what about the perimeter of triangle PQR? Is it MNO? What about the perimeter of triangle MNO? And you say, well, they're congruent, identical in every way, therefore they would have the same perimeter. Here's another nice question. Here's a real typical kind of things. You ought to pause that video, get a look at it, and see what kind of things you can equate. Because we've got to write some kind of equation. But I'm going to jump right in and tell you about it now. I hope that you've already thought about it. It tells me a couple of things about triangle PQRS, but it only tells me one thing about triangle ABC, that angle B is 90 degrees. And I would be telling you, well, who does angle B correspond with? And just by virtue of this congruent statement, we should know that angle B corresponds with angle R. And if I know that that's true, angle B is congruent with angle R, then I got an equation I could write. R, 10x plus 20 must be the same as 90 degrees. We'll solve that little equation. Got 10x equal to 70, subtracting 20 from both sides. Divide both sides by 10, and I'm convinced that x is equal to 7. But interestingly, it asks for the value of x, and that's easy enough. But then find the measure of the other angles in triangle ABC. Well, I'm going to try to figure out about triangle PQR first. I think if I do that, that would be a good idea. If x is truly 7, what about the measure of angle Q? And if x is 7, that'd be 6 times 7, there's 42 minus 2, that'd be 40 degrees there. What about the measure of angle R? Oh yeah, R was equal to congruent to angle B, but let me check on that. If x were truly 7, 10 times 7 would be 70, plus 20, yeah, angle R is 90 degrees. So what do we know about the measure of angle P? Oh, I'm sorry, QRS. What do we know about the measure of angle S? I apologize. And we don't have the way to relate with it here, but probably you recognize, like that you've learned in some other classes, the angles of a triangle add up to 180 degrees. We're going to prove that later this week. And if that's maybe later today, the angles of a triangle add up to 180 degrees. These two add up to 130, so that angle would have been 50 degrees. But it does talk about the measure of angle ABC. Let's go through there and do that quickly. Measure of angle A, since A is congruent with Q, and Q was 40, the measure of angle A would have been 40. Measure angle B, yeah, B was 90. And the measure of angle C, well, angle C matches with angle S, and we found angle S to have been 50, so I declare angle C to also be 50 degrees. Now, you guys got an assignment to look at.